Here we go. Lesson 2, two-dimensional momentum. We're going to go with angles shortly. We're going to start, though, with a nice review, everything in a nice straight line. I like example 1, I like example 1, I like example 1. Example 1 is a nice question. It says this: a 30-gram bullet moving at 250 meters per second strikes a 5-kilogram wood block at rest and sticks into it. If the bullet and the block move together after the collision on a frictionless surface, did they say collision? This is a job for conservation of momentum. Write a momentum equation. B, find the speed of the block after the impact. C, find the heat energy created during the collision. Oh, okay. Yeah, all the work and energy stuff is still fair game. I'm going to call the bullet B. I'm going to call the wood block W for wood. Unfortunately, B bullet and B block don't work very well, so I'll use B and W. Okay. A says, write a momentum equation. Is there a collision? The sum of all the momentum before the collision equals the sum of all the momentum after the collision. There's my momentum equation. I start here. Colin, what does B want me to find? Okay, so now I'm going to break this down. So I'll do that down here. Before the collision, what's moving? The bullet, the wood, both, or neither? I've heard both and I've heard bullet. Someone needs to convince me that someone else is wrong. Devin, can you read that to me right there? Okay, so before the collision, what's moving? The bullet, the wood, both, or neither? Before the collision, what's moving? We're doing initial first. Okay, so it's going to be momentum of the bullet initial. Okay. Bam! They collide. Every collision, boys and girls. After the collision, what's moving? The bullet, the wood, both, or neither? Both. Stuck together or separate? You're awake now, though. This is really our momentum equation. And again, Jake, notice how careful I'm being with vectors to remind myself I better pay attention to direction. And now, for the rest of your physics career, we pause and we say, hey, are there angles in this question? Everybody say no. What do I mean by angles in this question? Stuff like that, where you're banking off something, okay? We're going to get to that today, and it's going to be considerably more involved. But are there angles in this question? Everybody say no. So we can go straight to just writing the equations. Momentum is what times what? So this is going to be mass bullet v bullet initial, when they collide, equals mass bullet plus mass wood v final. And Colin already said, I think they're asking us to find V final. And because this is all in a nice straight line linear, we can just divide to get the answer by itself. We don't need to add tip to tail or anything like that. So V final is going to be the mass of the bullet, velocity of the bullet initial, all over mass of the bullet plus mass of the wood. You know what, Mr. Dewick? Since you can, why don't you be clever and go like that, and now you have more room to write intelligibly. And I'm going to plug in numbers. Mass of what was the mass of the bullet? 30 grams. How many kilograms is that? 0.03. Good. Speed of the bullet, this one's not going very fast. It's not even going faster than sound. Divided by, what was the mass of the wood? You know what? I'm going to add these together in my head. 5.03. Is that okay? What's V final? 1.491, I'll go 1.49 meters per second? Okay. So there's B. C says, find the heat energy created during the collision. What are they asking me to find here? You know what? That's a job for conservation of energy. KE initial plus PE initial equals KE final plus PE final plus heat. Are we starting on the ground with everything? Yeah. Are we ending on the ground with everything? Yeah. Okay, the bullet's in the air, but is the bullet changing height at all? So is there any change in potential energy? You know what? That's kind of nice. How would I get the heat by itself? So heat is going to be the initial kinetic energy of the system minus the final kinetic energy of the system. Whatever's missing must have been turned into heat. Kinetic energy, by the way, is not conserved. Otherwise, kinetic energy initial and kinetic energy final would be equal. You actually, well, in any car accident, of course kinetic energy is not conserved because your final kinetic energy in a car accident is always 0. And your initial is always not 0, otherwise you would have a car accident, right? Total energy is conserved, but most of it goes into heat. How much in this case? Well, we have to be a little bit careful here. Kinetic energy is what? What's the equation? Okay, half mv squared. Now, initial, it's going to be a half. Initially, Devin, what's moving? Oh, so the mass I'm going to put here is 0.03. Initially, what's the velocity speed? 250 squared minus, and what's my final kinetic energy? It's still going to be a half. What's my final m? 5.03. What's my final v? So I like this question, I like this question, I like this question in that I can almost guarantee, I will guarantee on your test, you'll have a question that involves both momentum and energy. And wow, that's kind of nice. I'm combining two separate topics because they're not that separate, it turns out. 0.5 times 0.03 times 250 squared minus 0.5 times 5.03 times, answer button, squared. Did I type that in right? Sure. Looks like 932 joules of heat. Is that okay? Now, we could also do this later on at angles, and the nice thing is energy is a scalar. Then I could ignore the angles, but I need to use the angles in the momentum section. This is why I like energy so much. It's so much nicer to handle. This is going to be fairly mathematically intense. Oh, example 2. The diagram below shows 2 pop cans of unequal mass. It looks like one has a mass of m and the other has a mass of 2m. Initially at rest, you know, I would probably underline the word at rest. An explosive charge is detonated between them. Boom! And the cans fly apart. What can you say about their velocities after the explosion? Using principles of physics, explain your answer. Yeah?
The block with m is accelerating.
I gotta say, not accelerating. We're talking velocities.
The velocity of m is 2 times bigger than 2.
Oh, he did the whole thing. He said the lighter can is going to go faster than the heavier can, and because the mass ratio is 2 to 1, the lighter can is going to be going twice as fast as the heavier can. I agree with you. Let's prove it. And you know what? Let's prove it with no English. Is there, Colin, is there an explosion? Oh yeah. This is a job for conservation of momentum. So I'm going to start out by going like this. Devin, before the explosion, what's moving? Mass 1, mass 2, both, or neither? So what's my initial momentum? As a number, please. Which also means my final momentum is 0, but since I have stuff moving, I'll break it apart. I'm going to say it's going to be the momentum. Let's call this mass 1. Let's call this mass 2. The momentum of object 1 plus the momentum of object 2. Or, based on what Leonard said, I guess I could also write it this way. Negative momentum 1 equals momentum 2 if I minus the momentum 1 over. Momentum is what times what? Oh, so this is going to be negative mv1, and this is going to be 2m v2. Hey, is there an m in everything on the left-hand side? There is. Is there an m in everything on the right-hand side? There is. What can we say about those m's? So, what is this saying? Oh, that's not an I, that's a 1. First of all, the negative tells me that these two cans are flying in what? Opposite directions. And the first can, the lighter can, is flying twice as fast as the second can, which is what Leonard said. But there's a lovely algebraic proof with no English. Okay. Some terminology. We're going to have two main types of collisions. There's collisions where masses stick together, tackling. A car crash if the wreckage entangles. A bullet entering the block and sticking. And then there's collisions where the masses bounce off of each other. Body check. Curling. Billiards. Pool. We have names for those. An inelastic collision, the masses stick together. An elastic collision, the masses bounce off each other. And here's how I remember it. An elastic collision, I always think elastic, rubber band, rubber bounces. Oh, they bounce off each other. Inelastic, stuck together. I will use those two words in questions. In other words, you may see a question that says they collide inelastically. That's my way, Devin, of saying stuck together, both moving after the collision. Or I might say they collide elastically. That's my way of saying they bounce off of each other. Now, I also wrote some subnotes here. You'll notice in all collisions, momentum is conserved. There's a special type of collision called a perfectly elastic collision where the masses bounce off and kinetic energy is conserved. That used to be important on the provincial exam. I'm really going to say scribble that out, scribble the word partly, scribble the word completely. I really want you to know the terms inelastic and elastic, and I want you to realize that kinetic energy is not conserved. Total energy is conserved. Momentum is conserved. But you don't need to get into all that stuff there. I have a video exercise for you. We're going to see some collisions. And your job is to see if you can decide which car, there's going to be two little cars on an air cart, which car has a larger mass. We're going to watch the video with no sound first, because he announces what the answer is in the videos, and then we'll watch them again to see if we are correct. So put on your thinking caps, or in Quinn. Okay. We were correct, by the way. Now let's go two-dimensional. Here's where you want to turn your brain on. Here's where we're going to kick it up a notch. A 60-kilogram hockey player traveling 2 meters per second towards the north. Everybody underline the word north. Collides with a 50-kilogram player traveling at 1 meter per second toward the east. Everybody underline the word east. The two become tangled together. With what velocity will they move after the collision? A little note, this is inelastic because they stuck together. So I don't have the hockey player body checking. For some reason, he's wrapping up and they're sticking together, which I know is a penalty, but I wanted it on ice so we didn't have friction. Okay? In case you're wondering. Here's the idea. Is there a collision? Well, then this is a job for conservation of momentum. The sum of all the momentum before has to equal the sum of all the momentum after. That hasn't changed. You know what else hasn't changed? Before the collision, what's moving? Mass 1, let's call this mass A. Let's call this mass B. Before the collision, what's moving? Mass A, mass B, both or neither? Oh, both. Okay, so that's going to be momentum of A initial plus momentum of B initial. Bam! They collide. Got you mid-yawn. I even look. Come on, you got to be ready. After the collision, this is going to be a fun unit. After, by the way, my apologies to those of you who are watching this on YouTube. The headphones, yeah. I get great comments on these ones. Oh, geez, you terrified me. Well, I'll help you learn. After the collision, what's moving? Mass A, mass B, both or neither? Stuck together or separate? Okay. And now I pause. Does this question have directions and angles? We're going to dulp. Now we're going to dulp. So momentum A, what direction is he traveling? North? Yoink. How big is that vector? Well, momentum is what times what? What's his mass? 60. What's his velocity? So this is going to be 60 times 2 or 120 long. You can either put both numbers there or you can just do the math 60 times 2 and put the momentum there. But what goes on the vector is the momentum. Wham, they collide. You know what? I should probably draw a compass rose here because Lord knows I've screwed that up before. The second hockey player B, what direction is he traveling in? East, you say. How long will this vector be? Well, it's going to be mass times velocity. It's going to be 50. Jordan, you know what? I've got a hankering to add these two vectors together. Any suggestions on how I might add them together? Draw them how? Tip to tail, you say? So, and although my little DALP sketch is terrible to scale because the 120 and the 50 look the same length, I'll try and draw my triangle a bit more to scale. I'll draw the 120 a little more than twice as long as the 50. I think it'll look something like this. Yeah? What's the resultant? I guess both of them tangled together move off in that direction. Thankfully, Jake, this is a right angle. Yay! So I can bring out Pythagoras. If it wasn't a right angle, cosine law and sine law. In fact, it'll almost always be cosine law. I'm going to call this momentum both. I'll put the variable on there. So I can say this. Momentum both squared equals 120 squared plus 50 squared. Right? 120 squared plus 50 squared equals, I was really nice. I made this one work out evenly. I won't try and do that again because it's a pain. But I think this one, you get the final momentum of both is 130. Don't forget the square root. Right? So I end up with this. Momentum, both final, kilogram meters per second. And that's the magnitude of the momentum. I'll do the direction in a second. But that's not what this question asked. What did this question want me to find? Did it say, find the final momentum that they move off together? Lewis, what did it ask me to find? Find the... Oh, if I know a momentum, how can I find a velocity? Momentum is what times what? Mass times velocity. So are you saying if I divide this by the mass? Which mass? Mass of both in this case, because it is the momentum of both. Okay? So the velocity, and now I'll bring my vector notation in, is going to be 130 divided by 60 plus 50. It's going to be 130 divided by 110. And I get 1.18 meters per second. Except that's not the velocity. That's a speed. How do I turn a speed into a velocity? I need a direction. Oh, I got a triangle up there. You know what? I think what I really want is that one there. By the way, that angle there, north of south, east of west, what of what? East of north. Let's get the angle. Which trig function? Oh. TOA. Which trig function is that? Tan. Tan theta equals opposite over adjacent. By the way, you'll notice way more work when there's angles. I think when they were in a nice straight line, it was like 4 lines, 5 lines, Bob's your uncle, and you're done. Here, we got to be way more careful. And this is a right angle. Shift tan of 50 over 120. I get 22.6 degrees east of north. This was enough work. I'm going to do my box of triumph. Oh, took a while. I would argue, though, Mac, I haven't done anything new here. I did say, is there a collision? This is a job for conservation of momentum. I did ask, before the collision, what's moving? After the collision, what's moving? I did say, wham, they collide. But then I said, okay, angles, it's always been a vector, but up until now, the worst I've had to have you deal with is make one negative and one positive. But we got angles, we better be doing tip to tail. Let's try another one. A car weighing 1,500 kilograms moving at 12 meters per second due west collides with a 2,400 kilogram truck that is moving at 16 meters per second due north. And let's assume the wreckage sticks together. With what velocity does the combined wreckage move off after the collision? By the way, I realized that on pavement, very quickly, the final velocity would be 0. So I'm talking about the velocity the instant after the collision. Okay? That's why the last question, Jordan, I did hockey players on ice, so I didn't have to address that at that point. Jordan, did I say collision? What's this a job for? Conservation of momentum, not impulse. Could be. It could be ice, and that's why they collided. Now, to be honest, usually already now I start asking, are there angles, are there angles, are there angles, are there direction? You know what? I would probably draw this, and I would be saying to myself, I better be dulping and adding vectors. By the way, if I like this question, like this question, like this question. If I gave you this question, the problem is a lot of kids, when they get to this line, Instead of doing the trig, they just go, oh, mass times velocity, mass, divide by mass of both. Understand, if this was a 7-mark question, I give you 1 mark for that, I'd give you 1 mark for that, and I'll give you 0 for everything else, because everything else is garbage. You'd get 2 out of 7. The most common mistake on these is kids solve linearly what they should have solved with vectors. Don't do that. Hey, before the collision, what's moving? Car 1, car 2? You know what? I have a car and a truck. How about C and T? That works. I won't bother labeling them. I'll just use the C. So before the collision, what's moving? The car, the truck, both, or neither? Both. So I'm going to have momentum car initial plus momentum truck initial. I could have done it mid-yawn again. I should have. Would have been great. Wham! They collide. After the collision, I am merciful. Am I not merciful? After they collide, what's moving? The car, the truck, both, or neither? Both? Stuck together or separate? By the way, fancy word for stuck together? Fancy word for stuck together? Inelastic. This is going to be almost identical to the one that we just did. If you feel comfortable going on ahead on your own and meeting me at the end, you can. I'm going to keep talking and walk you through it. But if you feel like, oh, I think I can do this one, feel free to try. Oh, there's directions. I better be really, really careful. So we have a car moving due west. Now, what goes on this vector? Not the 12, not the 1500, the momentum. 18,000. Plus, truck is moving due north. What goes on this vector? Not the 2,400, not the 16, the momentum. 38,400. Hey, Jordan, I want to add these vectors together. Have you got any suggestions on how I might do that? Draw them tip to tail. Now, I like to try and go roughly to scale. 38,400 is about twice as big as the 18,000. So I'm going to draw my triangle over here, and it's going to look like this. Yoink. And I tend to draw my vector diagrams big. I've learned if they're big, I make less mistakes. Yoink. I guess the resultant is, there's the momentum final of both. Yay, right angle. Pythagoras. $18,000 squared plus 38,400 squared. 18,000 squared plus 38,400 squared. Don't forget to square root. That's not the final momentum. And I get 42409. Of course, that's not what the question wanted me to find. Jake, what did this question want me to find? Final momentum? No. What did this question? Oh, if I know a momentum, how can I find velocity? Momentum is what times what? Oh, so you're saying divide by the mass? Which mass? Since they're stuck together? Both. If they weren't, it'd be the mass of whatever object I was looking at. But they're stuck together? Okay, so the velocity final is going to be 42409 divided by 1,524. This number, I'll use my answer button, divided by 1,500 plus 2400. 10.9 meters per second. This is a pretty, by the way, this is a pretty bad collision. If you run the numbers, this is probably serious injury in this collision. Except that's not a velocity. That's a speed. I think I did put in brackets magnitude and direction. Yes? So let's find a direction. Yoink. That angle there, what of what? North of south, east of west, what of what? West of north? Okay. Which trig function? Opposite. Oh, this one's going to be tangent again. That's kind of convenient. Tan theta equals 18,000 over 38,400. .1 degrees. Whew. So the of part, this part, the second part, is always going to be either the vertical or the horizontal line that it touches. So it's going to be go north, go west of north to get to there. That's how it works. Good question. Example 6. I like example 6, I like example 6, I like example 6. Example 6 is a nice question. In fact, you know what? On your test, you're going to have 2 or 3 collisions at angles or explosions at angles. Only one of them is going to be a right angle. Sorry. The others are going to be, fancy word, oblique angles. Yucky angles. Okay. I think we'll get through one of these. You ready? What's this question want me to find? VF. Is there a collision? Are there angles? This is a job for conservation of momentum, and we're going to be adding some vectors together. I'm going to start out the same way, Jake. The sum of all the momentum before equals the sum of all the momentum after.
Is it always going to be like that?
If it's a collision or an explosion, this is a job for conservation of momentum. Then I break it down further, Tyler. Looking at this picture, before the collision, what's moving? Mass A, mass B, both, or neither? Oh, so it's going to be momentum of object A initial. Bam! They collide. After the collision, what's moving? Mass A, mass B, both, or neither? Both. Stuck together or separate? So momentum A final plus momentum B final. That hasn't changed at all since what we've been doing since Physics 11. But now, Rob, here's Physics 12. Rob, are there angles? Then what I'm going to do is I'm going to draw a picture of each vector underneath each label here. So it looks like the momentum of A initial from this looks like it's straight sideways. That's kind of nice. So I'm going to say, okay, that. And how big? Mass times velocity. 5 times 1.2, which I think is 6. Yes. Wham, they collide. Looks like mass A goes off in that direction. I don't think I have any numbers to put on it, but I can certainly sketch it from the picture. Plus. And it looks like mass B goes this way. What's the velocity of mass B? 0.9. What's the mass of mass B? From the picture. 5. So I think if you go mass times velocity, 4.5. Oh, and I'll just label this as momentum A final. Which side do I have two vectors to add? The right side? Jordan, I'd like to add those two vectors together. Any suggestions for how I might do that? Draw them. Now here's the nice thing. Look up, look up, look up, look up, look up. This is the important thing. When I add these tip to tail, I know that if I add momentum A to momentum B, the answer has to be a straight sideways vector 6 long. In other words, that tells me how long to draw those two little vectors. It's got to look something like that. Oh, one more thing. Looks like this angle right here is 29 degrees, which means don't write this next bit down. I'm really going to gum my diagram up. This angle right here is 29 degrees. And then, seest thou the zenith? Which angle is 29 degrees inside the triangle? Bottom right. Okay? I don't want to have all this junk on my diagram, so I'm going to erase it, but I've walked you through the argument. Is there a right angle here?
Yeah.
Really? Where? Is there a 90-degree angle there anywhere? No.
It's like that.
I can't assume that it's 90. Might be. So can I use SOHCAHTOA? Sine law or cosine law? Which one? Well, I always check sine law first, and you might recall sine law, I'm looking for a pair. Nope, no pairs, it's cosine law. And it will be almost all the time cosine law. Okay? What's the cosine law? Mac was clever enough to search for his formula sheet. The cosine law, no, I'm serious, you need to be able to find it somehow. Cosine law, Mac, goes like this. Momentum of A squared equals 6 squared plus 4.5 squared minus 2 times 6 times 4.5 cos 29. Please tell me I gave you the whole page. Whew, I did. So we're going to need the whole page. I can go straight to my calculator for this, thankfully. It's going to be 6 squared plus 4.5 squared minus 2 times 6 times 4.5 cosine 29. Let's make sure I type that in right, because there's plenty of room to make mistakes here. What the? Oh, square root. Which looks about right. This does definitely seem shorter than the 6, which is why when I first saw that 9, I went, what the? No, it's got to be shorter than the 6. Oh, square root. I get almost 3 exactly. 3.003. Oh, is this my final answer? No? I'll carry some extra sig figs. So the momentum of object A final is going to be 3.00342. This isn't what they wanted me to find. What did they want me to find? Oh, a velocity, you say. If I know a momentum, how can I find a velocity from there? Oh, momentum is what times what? Mass times velocity. So if I want to find the velocity of object A, it's going to be 3.0042 divided by, what the heck was the mass of object A? 5. .601. Sorry, 0.601. I said that totally wrong. 0.601 meters per second, except, that's not a velocity. That's a speed. If I want to make it a velocity, what direction? By the way, this direction here, north of south, east of west, what of what? Stop, don't call it out. So ready, Carol Ann? We would go like this. It's going to be of that. What is that? You know what? We should have drawn a compass rose on here. So it's going to be of what of east? North of east. That's how it works. Good. So I'll leave a space. North of east. All right, let's find theta. Can't use tangent. This is not SOHCAHTOA. It's going to be sine law. Wait a minute, Mr. Dewick. I thought you said you needed a pair for the sine law. I do have a pair now, both of those, because I now know momentum of A. So it's going to look like this. Sine of this over that equals sine of this over that. It's going to look like this. Sine of mystery theta over 4.5 equals the sine of 29 over 3.00342, which is why I carried all those extra sig figs. Is this one fraction equals one fraction, Mr. Dewick? Wow, are we coming full circle for the beginning of the year or what? I guess sine theta is going to be 4.5 sine 29 divided by 3.00342. Whew. 4.5 sine 29 divided by 3.00342. What the? Oh, that's the sine of theta. That's not theta. How can I find theta? By the way, are you seeing how many sloppy mistake possibilities there are? This is why I said this is the second toughest question of the year. The toughest question of the year is of a similar difficulty, but it's about 5 more lines. So there's just more room to make mistakes. Shift sine. Yes? 46.6 degrees. No, did I what? 3.00342. Oh, 6 there? Here? Oh, here? Oh, I see what you're saying. But you know what? I used my answer button, so it didn't matter. That's why, by the way, that's why I always use the answer button, because I write stuff down wrong all the time. Thank you, Jake. Now I know where you're going. 46.6 degrees. That's as tough as it's going to get. Now, I'm going to pause here. We're going to continue with this tomorrow, but for 10 minutes left, you can certainly now do number 1. Number 5. I thought I put more right angle ones in here. Number 10. Yeah, here, I knew I'd added some right angle ones. Number 11. And if you haven't finished the homework from lesson 1, you can work on that because I'd love lesson 1 handed in today.